In the beginning, nearly 13.8 billion years ago, there was nothing but a dot in our observable universe, portion of the universe we can see and discover. Matter and space of the known universe was gathered in a dense point called singularity. First, let us know what is singularity. In scientific terms, a gravitational singularity, or space-time singularity, is a location where the quantities that are used to measure the gravitational field become infinite in a way that does not depend on the coordinate system. In other words, it is a point in which all physical laws are indistinguishable from one another, where space and time are no longer interrelated realities, but merge indistinguishably and cease to have any independent meaning. When suddenly it blasted, it kept expanding after that. What if our universe started shrinking and convert again in singularity? The part of the universe we can see becomes smaller because of this, and depending on the universe, galaxies may not be intact. An expanding universe means that things are moving away from us. An accelerating expansion means this is getting faster every day. There are galaxies that are moving away from us at speeds faster than the speed of light. They can do this because the space is moving, not them. This means that light from us will never get to the other galaxy. The part of the universe that we can see shrinks every day because of this. 10 to 35 seconds after Big Bang. At this era, there was nothing but soup of some particles AMD energy. The forces called strong nuclear and weak nuclear force were first separated at this time. There was a lot of virtual particles of matter and antimatter. A real particle, which acts opposite of the normal matter and which is created in CERN lab, which kept on forming, colliding and disappearing. After this, there come the four forces out of this in the universe. 1/1,000,000th of a second after Big Bang. At this time, all matter was heated and was forced to spirate from each other by heat energy acting on them. All the forces got separated. The temperature now was 1014 kelvins. It was got enough to convert energy into matter and form subatomic particles. Some of these types of subatomic particles formed are bosons, which is named after Indian physicist Satyendra Nath Bose, quarks, which was independently discovered by two members, Murray Gell-Mann and George Zweig, and is the constituents of protons and neutrons. Quarks, however, are of many types, whose names are simple and weird. Up, down, strange, charm, top and bottom. After 1/1,000,000th of a second after Big Bang Mao, due to expansion of universe, it cooled. It was not able to generate quarks, antiquarks and leptons. Some particles came together and collided to form fat particles like hadrons, which live a short life. The collision process started and many particles became big and small and formed many molecules of gases after this. The gases formed at this time were hydrogen, helium, and lithium. Now, a second has passed. The universe became opaque. There was nothing but small particles moving and colliding to each other. Moving electrons scattered photons, light waves, which became electrons back again. Protons became independent and gathered electrons and neutrons to become atoms. This went for about 120,000 years. Then there was no collision till 380,000 years, 90 million years after the bang. At this period, the opaque dusts in the universe stated to gather by the gravitational interaction between them. It was after 10 million years when the first stars formed, 16 billion years after Big Bang. In this period of time, some of the oldest stars began to die. Some stars exploded into supernova and emitted large amounts of dust and gases in space. Due to these materials, new stars began to form out of supernova, some stars shrinking due to its own gravitational pull and became a very dense point of gravity called black holes. Even light is unable to escape from a black hole. Some stars began to shrink, but the energy of particles was stopping it. The electrons and protons inside it collided from neutrons. They eventually became neutron stars. Neutron stars have electrical fields inside it. As a result, they also have magnetic fields. Most neutron stars are pulsars, which rotate at high speeds and radiate particles. Some stats didn't turn into supernova. They grew bigger, and gravity was making them shrink. They started to get denser. Sometimes small explosions took place that eventually emptied the star. This is typed as white dwarf. And some made new things in the universe. Some intense clouds began to rotate in its axis. It grew bigger and bigger by collecting other dusts by gravity. Some stars formed inside those dusts, and this formed huge celestial bodies called galaxies. The Big Crunch is a hypothetical scenario for the ultimate fate of the universe, in which the expansion of the universe eventually reverses and the universe recollapses, ultimately causing the cosmic scale factor to reach zero, an event potentially followed by a reformation of the universe starting with another Big Bang. The vast majority of evidence indicates that this hypothesis is not correct. Instead, astronomical observations show that the expansion of the universe is accelerating rather than being slowed by gravity, suggesting that a big chill is more likely. However, some physicists have proposed that a Big Crunch-style event could result from a dark energy fluctuation. The theory dates back to 1922, with Russian physicist Alexander Friedman creating a set of equations showing that the end of the universe depends on its density. It could either expand or contract rather than stay stable. With enough matter, gravity could stop the universe's expansion and eventually reverse it. This reversal would result in the universe collapsing on itself, not too dissimilar to a black hole. The ending of the Big Crunch would get filled with radiation from stars and high-energy particles. When this is condensed and blue-shifted to higher energy, it would be intense enough to ignite the surface of stars before they collide. In the final moments, the universe would be one large fireball with a temperature of infinity, and at the absolute end, neither time nor space would remain. If our universe started shrinking, it would be a profound shift from the current understanding that the universe is expanding. The consequences of such a change would depend on the rate and the physical mechanism behind the contraction. Theoretical studies have explored various scenarios, including the possibility that what we perceive as the expansion of the universe could be an illusion. If the universe were to start shrinking, it could lead to a reverse of the processes observed in the expanding universe. Galaxies might begin to move closer together, and the cosmic background radiation would shift towards the blue end of the spectrum, blue shift, instead of the red end, redshift. Maybe the universe isn't expanding at all. Maybe everything is actually just shrinking, so it looks like it's expanding. Turns out, scientists have thought of this. There are some people who would have you believe the universe is expanding. They're peddling this idea. It all started with a bang, and that expansion is continuing and accelerating. Yet they can't tell us what force is causing this acceleration. Just dark energy, or some other J.K. Rowling-esque sounding thing, otherwise known as the acceleration that shall not be named, and it shall be taught in the class which follows potions in third period. I propose to you, faithful viewer, an alternative to this expansionist conspiracy. What if distances are staying the same, and everything is in fact shrinking? Are we destined to compress all the way down to the microverse? Is it only a matter of time before our galaxy starts drinking its coffee from a thimble, or perhaps sealed in a pendant hanging on Orion's belt? So, could we tell if that's actually what's going on? The first horrible and critical assumption here is that shrinking objects and an expanding universe would look exactly the same, which without magic or hand-waving just isn't the case. But you don't have to take my word for it. We have science to punch holes in our shrink-truther conspiracy. Let's start with distances. If we assumed the Earth and everything on it was getting smaller, we'd also be shrinking things like meter sticks. In the past, they would have been larger. If everything was larger in the past, including the length of a meter, this means the speed of light would have appeared slower in the past. So was the speed of light slower in the past? I'm afraid it wasn't, which really hobbles the shrinky-dink universe plot. But how do we know that? You've probably seen spectral lines before, or at least heard them referenced. Scientists use them to determine the chemical composition of materials. A changing speed of light would affect the spectral lines of distant objects. And because some people are just super smart and were able to do the math on this, we know that when we look at distant gas clouds, we find the speed of light has changed no more than 1 part in a billion over the past 7 billion years. Shrinking objects would also become more dense over time. This means that the universal constant of gravity should appear smaller in the past. Some have actually studied this to determine whether it has changed over time, and they've also seen no change. If objects in the universe were shrinking, the universe would actually be collapsing. If galaxies weren't moving away from each other, their gravity would cause them to start falling toward each other. If they were shrinking, assuming their mass doesn't change, their gravity would be just as strong, so shrinking wouldn't stop their mutual attraction. A universe of shrinking objects would look exactly opposite to what we observe. So, good news. We're pretty sure that objects and us and all other things in the universe are not shrinking. Hope you loved it and got some knowledge.